Hey guys, thanks for watching my tutorials on Digital Srini channel on YouTube. And while you're here, please go ahead and hit the subscribe button. You won't regret it. Now, in the last video, we introduced XGBoost. We looked at what it was at a very high level and used it on Wisconsin breast cancer data set, which is structured data in an Excel or CSV file where you have one value that you need to predict and you have a whole bunch of attributes. Okay, now let's use XGBoost on a slightly different application. Again, if you're coming from microscopy or image analysis field, you probably would like to know about more tools for image segmentation, for example, or classification. So in this video, let's look at image segmentation or semantic segmentation, as they call it. Now, this is very similar to classification, right? Except we are classifying each pixel. In this example that we're going to use, each pixel can be classified into one of four. Okay, so as you can see, I have four different classes, or the blue, yellow, green, or red. So this is four different classes, and I'm classifying each pixel. So which means we have tremendous data, that need to be processed. Okay, and XGBoost is supposed to be optimized for speed compared to random forest. So let's hope that this actually gives us results in a quicker way compared to random forest. Now, of course, you need features, attributes to model a machine learning algorithm. For Wisconsin breast cancer data set, you have a whole bunch of measurements. What is the size? What is the radius? What is the perimeter? And all of that measurements that we use to model. Now, for image segmentation, where do you get these features? Well, we have to engineer our features. We have to generate our own features. You can use Gabor filters, you can use Gaussian smoothing, edge detection, and a whole bunch of filters, and you can put together your own features if you can engineer them. Or you can use features from a pre-configured network. So that's exactly what we're going to do here. So we're going to take the VGG16 architecture. This is our deep learning, right? So now I'm trying to mix these deep learning plus our XGBoost here, best of the both worlds. So what we're going to do is take VGG16 weights from imagenet. Okay, so imagenet is this database, and they've used VGG16 to train on a whole bunch of these 10,000 plus images. And now after the training, now you have the weights for this convolutional layers, right? So what we're going to do is chop off these convolutional layers and take those weights, which is basically nothing but digital filters, right? And use them as feature generators. We have done this in the past a couple of times, but again, it's worth repeating in case you haven't watched those videos. So use this VGG16 ImageNet as feature extractor and send those features through XGBoost and try to segment an image. That's the plan for today. Okay, so now let's jump in. And first of all, let me just show you what the how the images actually look like. Okay, so here is the structure. So I have a folder called images. Within this, I have subfolders, train images and train masks. Train images, again, these are the images I'm going to use for training. They're pretty big. In fact, I think these are 996 by 1024, tremendous amount of data. And I have train masks. Masks is, in fact, I should show you, here is, okay, so here is, let me minimize this so you can kind of see it a bit better. Okay, so on the left-hand side is the actual training image. On the right-hand side is the mask. And a mask where I painted pixels, like I literally used like a paintbrush tool and painted some of these in corresponding to the bright region and given them a pixel value of, what is this? A pixel value of 4 here. So the background is 0 or the dark is 0. This phase, this region, the grayish region has a value of 3 in my labels. Okay, so what is a label? Label is ground truth. So in this ground truth, my dark pixels have a value of 0. And something else has a value of 1, like this one has a value of 2, for example, this grayish region. So my goal is to segment these different looking regions, okay? Which is very hard using just histogram segmentation because this one requires a lot of textural information, for example. Okay, so this is my labeled image. If you wonder where did I get my labeled image, if you don't have a way of doing this yourself, well, go to www.appear.com, A-P-E-E-R. Go ahead and sign up. This is free for everyone. So go ahead and sign up, and within Appear, you can load your images and actually annotate this, or just go to appear.com/annotate to get more information on what it is. Okay, so either way, just sign up for Appear and you'll get these tools. You upload your images, and as you can see here, once you upload your image, you can select, okay, this is my class 1. Let me define all the regions belonging to class 1. Now I want to do class 2, class 3, and then you can download your image. That's exactly what I'm using here. Okay, so I have 8 such masks, right? 8 such masks corresponding to my 8 training images. That's it. And as you can see, all my masks are like only a subset. If I take my image number 7, sorry for spending too much time on this because this is important. Image number 7, and if I go to train masks, my mask number 7, so here is the corresponding mask. Okay, as you can see, I'm not painting every pixel, because if you have patience, go ahead and do that. I'm just painting only a few pixels. I'm like, okay, some pixels right there, some pixels right here. Obviously, the more training data, the better it is all the time. Okay, but most of the time we may not have the patience. And in fact, if you want to do deep learning, you probably are forced to label every pixel because you're using convolutional layers. Here we can drop the pixels that are not labeled, okay, which I gave a pixel value of 0. Okay, enough of that. Given that scenario, now let's jump into the code and hopefully things make sense here. Okay, so the goal is to segment our images. And by the way, one final thing that I have here is test images right there. Okay, I have a test image and I have a corresponding test mask. So if I actually, sorry, this is also important. If I open this test mask, this is a mask where I got every pixel kind of labeled. You can do this manually, or you can do this in an automated way, like where you use some other segmentation method to segment every pixel. But either way, this is my ground truth for this image. For this image, that's the ground truth. Okay, where I know exactly what each pixel belongs to. This is semantic segmentation. Why do I need this ground truth? So I can calculate the accuracy, because when I just do testing, segmentation, I need to find out what the accuracy is. So I compare against the ground truth, not just accuracy, but also IOU, intersection or union, which is the right metric for accuracy or model performance when it comes to semantic segmentation. So all of that, we're going to do it right now. Okay, hopefully in a quick way. I'll share the code, so don't worry about taking notes or taking screenshots for the code. Okay, I'll definitely share it with you. Check the link under description. It's on my GitHub page. Okay, now let's jump in. So the goal is semantic segmentation using XGBoost by extracting features using our VGG16 imagenet pre-trained weights. And I also mentioned annotate on appear.com, and this is what I'm using: TensorFlow 2.2, Keras 2.3, and Python 3.7. Although not many tricks. I mean, even if you have slightly different versions, it should work. Now, pip install XGBoost to install your XGBoost, and we are going to use XGB classifier. And these are all the hyperparameters you can define in the classifier. For now, I'm not going to define anything, which means I'm going to use the default values. But you can see, for example, learning rate. Why does it have learning rate? Because it uses gradient descent. Okay, and gradient descent, you have to define the learning rate, right? So this is certain hyperparameters make instant sense to you. For others, look at the documentation that these guys actually have. Okay, now get to the real code. All of this should be pretty straightforward to you, right? So we are importing NumPy, Pandas, Matplotlib for plotting, Glove for walking through the folders, and OpenCV to read the images, and Pickle to save or train model and also load it later on. And now from keras.models, let's import model because we're going to use VGG. Of course, if you want, you can use your own feature extractor. I forgot my video numbers, sorry, but go ahead and search for image segmentation using traditional machine learning, or using random forest on my under my videos, and you'll find a way of extracting features by not using deep learning, but by using your own features like Gabor and other features. Okay, so if you want to do that, you can also go ahead and explore that. And I'm going to import OS, and also finally keras.applications VGG16. I'm going to import VGG16. We'll see all of these in a second. This takes a second because it's importing the entire VGG16. Now let's go ahead and look at our folders so we can walk through these. Again, this is optional. I'm just curious in terms of how my folder structure looks like. Okay, so then you can go ahead and print this. So let's go ahead and do that. Again, I have 3 subfolders: test images, train masks. We already looked at it. I'm predefining my size of X, my image height and width, because I'm going to use that later on. That's it. I'm creating an empty list called train images because I would like to capture all my images into this empty list. Okay, so here I'm reading one image at a time under train images. I am reading these images right there using OpenCV ImRead. I'm resizing them. In this case, I'm not resizing them, but if you have images of different sizes, it's very important to do this step. Well, I said I'm not resizing. I'm truly not changing the shape of original images. They're all 1024 by 996. And because OpenCV reads images in RGB, this is optional. In fact, I can actually comment this step out and it makes no difference. Okay, but since it's there, let's leave it. All it's doing is converting RGB into BGR because OpenCV, the way OpenCV reads images. And after reading each image, I'm appending it and populating this train images list, meaning at the end of this, I'll have a list that's got 8 images. As you can see, my image train underscore images is a list of 8 images or 8 NumPy arrays. Well, let's convert this list into NumPy array because it makes it easy for us to work with. So let's do that. So now it is a NumPy array of 8 by 1024 by 996 by 3. This is basically my image size, and I have 8 images, right? 3 because we are reading them as color. And VGG, I believe, uses color, 3 channels. Let's do exactly the same with our masks. All I'm doing is reading all the masks and converting that into a NumPy array. Okay, so our mask size should exactly be the same. Train masks, I have 8, 1024 by 996, and it's a grayscale. It's a 8-bit image, so it's not 3 channels. It's a single channel, so that's why I don't have this 3 right there. So far, so good, I hope. Again, some of you may think that these are all trivial steps. Why am I covering? Most of my viewers range in in their skill set, so I really want to make sure if you are seeing this for the first time, you really understand this line by line. I try to add as much annotations as possible to my code, but again, it doesn't hurt to repeat things. Okay. These steps are optional. I'm just renaming my train images or copying that into Xtrain because it's very common to use Xtrain and Ytrain as part of our machine learning, right? I should have been better in naming this right from the beginning. Okay, Ytrain. Now, if you look at my Ytrain, it's only 8 by 1024 by 996, but we need the 4th dimension showing the number of channels. So I'm expanding the dimensions right there by adding one at axis 3. So now you can see my Ytrain is 8 by 1024 by 996 by 1. So now my train images and Ytrain have similar dimensions there. Okay, now let's come down and load the VGG model. And again, we already imported VGG16, and let's import that with imagenet weights. You can import with other weights if you want, but let's import this for this exercise, imagenet weights, and include top equals to false. What does that mean? Let's not include the dense layers. I'm just importing only the convolutional part of it. Okay, and the input shape is size X and size Y and 3, right? So what is the shape of my inputs? VGG16 is originally trained in I believe 224 by 224 images, but it doesn't matter. We can work with 1024 by 996 images as long as you're not including the dense layers. If you're including the dense layers, then the shape should match. Please remember that. Okay, so let's go ahead and import this VGG model with imagenet weights. There you go, we have it. Now let's go ahead and make all of these layers non-trainable. Otherwise, they're all trainable. Then it becomes a deep learning exercise. So I am setting all of these to be non-trainable, layer.trainable for each of the layers in my VGG layers as false. Now, if you actually print the summary of my VGG model, like we normally do, look at the summary. You see, this is my VGG. Input 1, 1024, 996 by 3, and then this is the first convolution, second convolution, max pooling. Con2D, max pooling. All of this, and down here, it should say total number of parameters are 14,714,688, but trainable, 0. Normally you have, 14 million. Normally you have these many million trainable parameters if you're doing deep learning. Now we are not doing any of that. Don't train anything. Just use the pre-trained weights. That's it. This is how you use this as a feature generator. If all of this is confusing, if you're coming from traditional machine learning, don't use this as feature extractor. Use Gaussian filters and edge detections and all that. Again, watch my video. I believe it's 67B, but please search for image segmentation using traditional machine learning videos. Okay, on my under my channel. Okay, so right now we have a VGG model imported, where we said we don't want to use, we don't want to train any of those. Now, let's take a subset of that. Okay, if you look at this is a pretty deep model. And down here, by the time it ends, your image is 32 by 31 by 512 dimensions. It doesn't make sense. You're changing the dimensions. Okay, there are tricks to handle with that. But what I'm trying to mention here is, look at block 1 conv 2, block 1 conv 2 right there. This is 1024 by 996 by 64. This 64 represents the 64 filtered images that you would get for each of these images of size 1024 by 996. After that, the dimension changes to 512 and so on. So I want to cut this part and only take up to this layer, the output of this layer. That's exactly what the next line is. Okay, so at this block 1 conv 2, okay, I'm defining a new model that cuts off at that position. Okay, so name model is not defined. So I thought I ran this line. Now let's come back and do exactly the same thing again, and hopefully this should work. There you go. And now let's do new model.summary. So you'll see that all we are doing is taking only the top 3 layers. That's it. Okay, 1024, 996, 3, this and this and this. So this would be the output. I hope this is clear. Okay, the input is our image. The output is 1024 by 996, the same size as our image, except 64 of them. This is 64 different featured responses from our images. This is how you generate features. Okay, so again, please go through this if it doesn't make any sense. Now, my features is basically when I apply my new model onto my training images. That's my features, right? I'm predicting using the new model onto my X-train. So these are all bunch of features. So at the end of this, let's give it a second. At the end of this, you should see features where you have 8 images, 1024 by 996, 64 channels or 64 responses, basically 64 of these features for each of these image. Okay, so that's it. We have our features. Now we can go ahead and train our XGBoost. But before that, again, like random forest, XGBoost also takes the structured data as input. So we need to kind of reshape our output into the right format. But if you're curious on how these filters look like, let's actually look at 8 of these, or 8 by 8 grid of these features. So all I'm doing is taking these features and plotting them so we can visualize them. Okay, so let's go to plots, and there you go, 8 by 8 grid, right? I mean, I'm doing 8 by 8 grid and looking at all the 64 features. Some of them probably we can increase the range to see, but hopefully you guys can see how these features look like. Okay, these are all the different responses or different filtered images or features, if you want to call them. Okay, so far so good. Let's move on to the next step. So let's define our X. What is our X? X is something, any machine learning, we have X and Y, right? Y is what we are trying to fit it to. X are all the features. So X is basically our features, right? The features we just extracted. I'm just reassigning these features to a variable called X. Now, my X has a dimension of 8 by 1024 by 996 by 64. I'm reshaping them so it's compatible for random forest or XGBoost. So if you look at X right now, it's still 64 features, but I collapsed all these 8 by 1024 by 996. That's pretty much it. So these are our X values, which means we need to do exactly the same for our Y. Okay, so let's do Y and reshape our Y. And now you see our Y also has these many, and you know, this is what we are trying to fit our X to. Now we are all set, and let's okay. So right now we are actually all set to go ahead and work with this data, but we have how many? 8 million, right? 81,059,232 pixels. This is tremendous amount of data, which is fine. Let's go ahead and fit it. But most of it is useless. Remember, if you have this label, most of this image is black, meaning I haven't labeled it. There's no point in using it. In fact, we should not be using it. Okay, so the next step is dropping all the pixels where I have a value of 0 and only using the ones with values 1, 2, 3, 4. So if you have a true label with a value of 0, reassign it to 1. I hope this makes sense to you. All I'm trying to do is make sure that I'm not including regions that are not labeled. If every part of your image is labeled, fine, you can go ahead and use it. But in this case, that's not true. So the easiest way I'm trying to do is combine my X and Y into a single data frame and then dropping values that are equal to 0. If you keep them separate, then how do you know which ones to drop from X, which ones to drop from Y? So the easiest way is combine. That's exactly what I'm doing. Okay, my data set is the same as X except in a data frame, pandas data frame. And my data set, I'm adding a column called label with values from Y. And now let's just print the unique values right there. 0, 1, 3, 4, 2. These are the values for our labels. Okay, 0, 1, 3, 4, 2, right? And we are going to drop 0 because the true labels are 1, 2, 3, 4. In fact, let's go ahead and look at the counts. You see my 0 has 78 million pixels unlabeled. So I need to drop this and use only the ones that are labeled. Again, all of this is appropriate only if you have partially labeled images. If you have images where everything is labeled, you don't have to worry about this. Okay, now I'm taking a subset of this data set where the labels are not equal to 0. That's pretty much it. This is how we are dropping this. Now, if I go ahead and do this, now we should not see anything for 0. All I have is only 3, 1, 2, 4. That's it. Okay, I hope that makes sense. What does this have to do with XGBoost? Well, data preparation is 99% of the work. Actual machine learning is the easy part. Okay. Now let's come back and define our X and Y again, redefine, because now we have a data frame with both X and Y, right? So, okay, my X for training is my data set where I drop the column label and I convert that into an array. Okay, this is in pandas data frame. I convert that into an array. Same thing for my Y. Y is basically the data set where with the column values label, convert that into a NumPy array rather than working with pandas data frame. Now, why did I do that? With XGBoost, with random forest, it works fine working with data frames. With XGBoost, it also works fine. But if some of the features have values of 0, one of the ways XGBoost optimizes is by dropping anything that it thinks is irrelevant. And it drops, for example, one of your columns, one of your features where all the values are 0. Then your column names or feature names get messed up. I hope this makes sense. During training, let's say it drops like 5 columns, okay? And your column names are different now for features, but then during testing, you have different column names. So it throws some weird error. So it's better to work with NumPy array, rather than pandas data frame, okay? Again, just based on my experience. Finally, we have everything ready. We have our X values as an array. We have Y values as an array. That's it. Let's go ahead and define our XGBoost. Again, from the library, I am going to use XGB classifier. If it's a regression problem, obviously you use regressor. Okay, so I'm using classifier there because we are classifying each pixel into one of these 4 values, 1, 2, 3, or 4. Now, let's do model.fit. In fact, let me open the task manager so we can keep an eye on how it is doing, how efficiently it's distributing. You do exactly the same exercise with random forest. You'll see that it's not that efficient in assigning tasks to different processors. Okay, so now let's go ahead and do model.fit. Let's go ahead and run that. And while it's doing it, because we have tremendous amount of data, this will take certain time. I'll pause the video, but I want you to have a quick look at how all of my, I believe 64 or how many ever of these are 100% utilized. So my utilization is 100%, and still it leaves room for my video. This will take a few seconds, so let me go ahead and pause this and continue the video so we can look at the results. Okay, so this is done. As you can see, everything is ramped down. So this is pretty fast actually. It took probably a minute or so with all this data. And it'd be interesting to see how long random forest actually does. And I'll leave that to you, even though I have those couple of lines here. I don't want to extend this video any further than it really needs to be. Okay, so now that we are done fitting this model, let's go ahead and save this into your disk. Okay, and for that I'm going to use pickle, so I'm going to dump that onto your disk, and we can go ahead and load this later. Again, this is optional, but of course this is necessary if you're going to put this in production mode. Once you train it and now you're segmenting it, it's better to save this model, right? So let's go ahead and load the model again. So now we have the new model. Now let's go ahead and read an external image. So now I'm going to use test images, okay? One of the test images, and doing exactly the same process here. Resize it, change the color because we did this for our input images, and then expand the dimensions. So if you look at this, you should see that my test underscore image, if I can find it, my test underscore image is one image, 1024 by 996 by 3. Okay. Now, what do we need to do? Extract features. How do we extract features? My new model.predict, right? So that's our new model. Our new model is basically the VGG pre-trained weights, except we only took the top 3 convolutional layers. That's exactly what we are applying here. New model.predict. This extracts the features from our new image, and now I'm going to reshape this into the right format for our prediction, for our model prediction, and now let's go ahead and predict it. Okay, I hope this makes sense. I'm just following the same things that we have done for training. So now the prediction is done. So if you look at prediction, I have these many, basically this is 1024 multiplied by 996, which means I need to reshape it if I want to look at it as an image. Okay, so let's go ahead and reshape it to the same size as the original shape right there. And let's go ahead and show this image. So plot, there you go. That's the segmented image. Okay, in fact, let's go ahead and dump it onto the disk so you can have a look at it. In fact, let's go ahead and look at it. Test images. This one is 360 segmented. There you go. And the test image, let's go ahead and delete this. Okay, so this is the 360, this is the segmented image. This is the, sorry. Let me open this one more time. Okay, so here, this is the segmented, this is the original. Not bad, huh? It can do better in these regions, but again, that's where more training data definitely helps. There you go. Okay. Okay. Now, visually, that's fine. How do we quantify it? How do we say, okay, this is 90% accurate, or how well did it do on one phase, one region versus the other? That's exactly why I have That's exactly why I have my test image and test mask, the ground truth, so we can extract this accuracy and other things. That's exactly what I'm doing down here. So for my validation image, exactly same things. If you want, you can go ahead and save it. But let's go ahead and predict, and let's look at the accuracy. Okay, so my prediction validation is right here, and let's go ahead and let's save this. I'm loading my truth image right here. Okay, truth is basically test1.mask, right? So this is my truth image, ground truth. So now all I need to do is compare my prediction validation against the truth. That's it. First, let's look at the accuracy, okay? How well the accuracy is. Again, I'm using matrix.accuracy score, but for truth and prediction, let's do that. And I got 93.8%. That's great. You see millions of pixels here, and I got about 94% accuracy on this one. I bet very close to even manual segmentation. If you give the same to 20 different people, I wonder how good the segmentation is between different manual annotators, if that's a word. So 94% accuracy is pretty good, but how well is it doing on the easy to segment regions versus the tough to segment regions, right? This is exactly why accuracy score is crap when it comes to semantic segmentation. This is why you need to use IOU, intersection over union. I made a video on this, so let's not dwell too much time on it. I'm using the mean IOU from Keras, and let's print out IOU. And well, overall, the mean IOU is 79 or 80%. Let's say 79% in this case is, that means it's telling me it's doing great on certain regions, but not good on certain regions. Like of these 4 different phases, some are easy, some are difficult. Now let's see where it's failing, possibly because of imbalance. You see, one of the regions, I don't have much of it. The others, I have a lot of it. But anyway, now let's actually extract. Again, I don't want to go through each line of this code. I have already done this in my IOU video. But what I'm trying to print out is IOU for class 1 is 96%. It's doing excellent for class 1. It's doing great for class 3, like 89% and 88% for class 4. But when it comes to class 2, it's not doing good. It's actually 42.4%. And class 2 is the tough one. Class 2 is, in case you wonder, class 2 is this region, this textured region right there. This is a difficult one. The easy ones are the bright ones. This gray one is easy, and the black is easy. These are class 1, 3, and 4. Class 2 is this textured one. Okay, which is, in case you wonder what that is, it's clay. This is a sandstone. So this is all quartz. This is pyrite, bright regions. Dark is void pores right there. It's easy to segment. These ones are difficult to segment. Okay, because their mean gray level is same as the mean gray level of this one. That's why I'm not getting good result on that specific phase. But if you do deep learning, I've done exactly the same thing on deep learning. I've done random forest. In fact, with Keras, I actually got like this accuracy in like 30s or so. So this is actually doing much better than anything else. This 42% is not a failure of XGBoost. It just reflects the complexity of segmentation for this specific sample. If I get much more training data, that definitely improves, especially if I balance that against all the other regions. Okay, I hope you really found this tutorial to be definitely long, because I know this is almost like 30 minutes or so, but definitely worth watching. And this type of semantic segmentation, you will find that this is comparable to unit, for example, especially better than unit if you don't have a lot of training data. If you want to do exactly the same thing using a unit architecture, you need a lot more training data, and most of us do not have that. So please think of XGBoost as your first option when it comes to classification or segmentation. Okay, and again, do not forget to sign up to apeer.com, apeer.com, where you can get all the free tools. You can annotate, and you can also use machine learning units and complex units for image segmentation and so on. So thank you again, and please subscribe, and let's meet again in the next video.